Remember where we finished up, right? We were talking about Hermitian matrices, and we said that any Hermitian matrix is unitarily diagonalizable, right? So that was our so-called spectral theorem, right? Any Hermitian matrix is unitarily diagonalizable. Okay. And the way we got it was by using Schur's theorem, which said that any matrix is unitarily upper triangularizable, right? So we got it. It was basically a quick consequence of Schur's theorem that every matrix is unitarily upper triangularizable. Okay. And what we said that we were going to do today was this thing about normal matrices. So normal matrices. And I think we said what normal matrices are. They are matrices that commute with their conjugate transpose. Right? So recall, right, A is normal means that A conjugate transpose. Whoops, that's not normal. That's anybody, right? That A commutes with its conjugate transpose. Okay, and we said that we're going to prove a theorem that says that A is normal if and only if A is unitarily diagonalizable. Unitarily diagonalizable. Okay. So, right, if you're Hermitian, you're unitarily diagonalizable. Okay, but it's not true that being unitarily diagonalizable means that you're Hermitian. Being unitarily diagonalizable is equivalent to this condition called normalness. Okay. So the proof of this is not too bad. So let's do the backwards direction. Okay. Let's suppose that A is unitarily diagonalizable. Okay. In other words, there exists a unitary U such that UHAU is some diagonal matrix. Okay. Right. Suppose you're unitarily diagonalizable. Right? That's what this says. Suppose you're unitarily diagonalizable. So you want to show that that AHA equals AAH. Right? That's what we want to show. So you say, okay, well, look, what's A? We have an expression for A, right? UHAU equals B. So what's A? A is going to be U, D, UH, right? So A equals U, D, UH. Okay, so all we need to do is check that AHA equals AAH, and it turns out to be just a calculation. So you go, shall I let you do it? Take 30 seconds and write down these two things and see that they look equal to each other, that they are equal to each other. Okay, turn to somebody nearby and say what you did, or... Connor, talk with Ethan. Fine. Okay, so let's do it. We want to see that AHA. Well, you got AHA equals AAH, right? So AAH, right? That's what we want to see, right? Well, when you take the conjugate transpose of a product, right, you're going to get the product of the conjugate transposes, but in the reverse order, right? Just like when you're taking a transpose, right? The transpose of a product is the product of the transposes in the reverse order. So we're going to get UHH, DH, UH, UDUH. Does that equal UDUH, UHH, DHUH? Okay. Of course, the double H's just cancel each other off because you're taking two transposes and two conjugates, right? Two complex conjugates. So those guys just vanish, right? Doesn't do anything, right? And so our question is, what else happens? What's UHU? What's UHU? I, right? Because U is unitary, right? So this vanishes. This is I. UHU equals I. And so our question becomes is UDHDUH equal to UDDHUH? Are those equal? Yeah, Connor.
So the operation between like the second and third line, why is the UHH the first thing instead of UH on the like the bottom?
Because when you take the transpose of a product, right? You get the product of the transposes in the reverse order. Okay, so the same thing's going to happen with the H. If you take the conjugate transpose, well, you get the product of the conjugate transposes, but in the reverse order. Okay, and so we're going to get UHH first. Okay. Okay, so this is our question, right? Is this true? And you see that it boils down to asking, does DHD equal DDH? Right? Well, is that true? That's definitely true, right? If you've got a diagonal matrix, right? If you've got a diagonal matrix, and you take its conjugate transpose, and then you take the conjugate transpose, right? If you multiply them in the reverse order, you're just going to get the magnitudes, the moduli squared down the diagonal, right? No matter which way you do it, right? So DDH and DHD are the same. Okay, so you don't have to worry, right? So our question is answered, right? So this is true, which is true since DHD does equal DDH.
We aren't doing DH equal.
Why?
Because it's diagonal and the entries are real.
Why are the entries real? Why are the entries real? Certainly if it was Hermitian, remember, then the eigenvalues are real. But we're not Hermitian anymore.
So if it's
Hermitian diagonal matrix, then all the eigenvalues. If it's, yeah.
If it's Hermitian, then all the eigenvalues are but we're not talking about Hermitian, right? We're talking about normal matrices, which are that Hermitian is like a special class of the normal matrices. Okay, so that's the backwards direction. Being unitarily diagonalizable causes you to be able to commute, causes A to commute with its conjugate transpose. Okay, so now let's go the opposite direction, right? Let's show if A commutes with its conjugate transpose, then A is unitarily diagonalizable. Which I can't spell today. Strangely. I used to be a good speller when I was a kid. Not anymore. Okay. Okay. So what we're going to do is basically follow the path of the spectral theorem, which is use Schur's theorem. Okay. Use Schur's theorem. So use Schur's theorem. Right. We know there exists a unitary U such that UHAU is upper triangular. Okay. Right. Right. Now, I claim that, in fact, T is diagonal. No, hold on. Okay, I will say that, but not yet. I claim that T is also normal. Right? T is itself normal. Okay, so let's see how that works out. Again, it's the same sort of thing, right? So consider THT, right? So we want to see that THT equals TTH, right? We want to see that THT equals TTH. So we just write it out. It's basically the same sort of game that we just played. So say, okay, well TH, right? So you get TH. T, right? THT equals UH, AH, U double H, and then UHAU. Right? I'm just, just using the conjugate transpose. Reverse the order, put the conjugate transpose is on. Okay. Okay. Again, we use the fact that U times UH is going to be the identity matrix. Right? So this is the identity matrix. We can drop it out. We get UH, AH, AU. Okay. If I did it in the opposite direction, T, TH, what do I get? Well, I get UH, AU, UH, AUH. Right? But that's UH, AU, UH, AH, U double H. Okay? And again, the UH drops out, and I get UH, AAHU. Right? Well, are those equal? Sure, right? Because A is normal, right? AHA and AH are the same thing, right? So you see that TTH and THT are the same thing. Right? So since A is normal, we see TTH equals THT. Okay, so T is normal. Yeah, Connor.
Why isn't AAH the identity matrix again?
It was true for U because U was unitary, right? U was unitary, but A is not unitary. A is just some matrix. The only thing we know about A is that AAH equals AHA. Okay. We don't know. It's not true for all matrices that A times the conjugate transpose equals the identity matrix. Only for unitary matrices. Okay. Other questions? Other questions? Okay. So okay. So now let's. Okay. Let me we'll see that in fact T is diagonal. In a second. Okay. We've got this normal upper triangular matrix. We'll see that in fact any normal upper triangular matrix is diagonal, and that will be the end, right? Because we were trying to show that A was unitarily diagonalizable, but what we'll see is that it's unitarily triangularizable, but the triangle, guys, is actually diagonal, so it's unitarily diagonalizable. Okay. Are you guys following? I feel like I've used too many words, but you're not. Okay. Okay. So we just need to show that if you are a normal triangular matrix, then you are diagonal. Okay, so here's the theorem, or here's the lemma. If T is a triangular normal matrix, then in fact T is diagonal. Okay, so the proof of this turns out to be just a calculation. It's not particularly interesting, but we'll do it. Okay, so let's do it. So we know that T looks like this, right? T11, T12, T1n. So let's say it's upper triangular. T22, T2, T2n, Tnn. Okay, so let's consider TH, right? So T normal implies that THT equals TTH. Right? THT equals TTH. Okay, so let's write out what that says, right? I take the conjugate transpose, T11, T12, T1n, T22, T2n, Tnn. I take the conjugates of everybody, and I multiply that by T. This equals the guys in the opposite direction, in the opposite order. Right? So T1, T1, T2, T2n, T2n, T11, T12, T1n, T22, T2n, Tn. Okay, so I just write it out. Hey, Connor.
Why does the notation change from like T12 is like in the column instead of?
Because what's TH? TH is the conjugate transpose. Right? So you take this guy, you transpose it, and you take the conjugates. Okay? Okay? Okay, so now consider the diagonal elements on both sides. Okay? So if we look at the diagonal elements, right? What is the diagonal? So here's a product, right? Here's a product. What is the 1-1 term?
T11 conjugate times T1.
T11 conjugate times T11. In other words, T11 modulus squared. Okay. What about on the other side? What's the 1-1 term on this side?
Same.
No.
It's T11 times
T11 modulus squared plus T12 modulus squared plus T1n modulus squared. Right? Because you take this row against this column. Right? Over here you got this row against this column, it was easy. You've got n terms to multiply.
All right. Yeah.
Okay? Okay. Now, second row, second column, here I'm going to get T12 modulus squared plus T22 modulus squared. And on the right-hand side, I'm going to get T22 modulus squared plus T23 modulus squared plus T2n modulus squared. Right? And I go all the way down, right? At the end here, I'm going to get T1n modulus squared plus Tnn modulus squared. And then on the right-hand side, I'm just going to end up with Tnn modulus squared. Yeah, come on.
What's the word after diagonal?
Elements. Sorry. Elements. Ethan, are you okay?
Yeah.
You don't look well. You look tired. You're all right. Okay. Okay. I have been up since around 2:30 because my daughter had the smallest one had a sort of like an asthma attack that lasted until it was time to wake up and beyond. So I have no sympathy for you, Ethan.
Is she okay?
Yes. Yeah. I just had to give her the medicine. I mean, I hope, hopefully, right? Yeah, I hope so. Okay. So okay. So you see what happens. Let's see what these equations give us. Well, look. T11 squared equals this thing squared. So I get rid of the T11 from both sides, right? And I see that T1, the modulus of T12 plus blah 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 plus the modulus of these, the sums of the moduli squared equals 0, right? So that tells me that T12 through T1n are all 0, right? Because the sums of their sizes are 0, right? So it tells me that T1, T12 up through T1n, these guys are all 0. Like from here to here, these guys are all 0. Okay. Then I go to the second row, and I say, okay, I already know that T12 is 0, so I'm going to get rid of that. And I cancel off the T22 from both sides, right? I cancel out the T22 from both sides, and I get that T23 through T2n are all 0. So this guy through this guy are all zeros. Come on.
On this one, there's 0. Why are there 0?
Well, because the sums of the squares of their moduli is equal to 0, right? These are all positive numbers. The moduli are all positive numbers. You have a bunch of positive numbers that add to 0, right? A bunch of non-negative numbers that add to 0. Well, they must all be zeros, right? So these guys, the moduli are all zeros, so these numbers are all zeros. Now, if I tell you that a squared plus b squared equals 0, right? What can you tell me about a squared? What do you know about a squared? It's got to be 0, right? B squared, it's got to be 0. Okay, and you keep on going all the way down, and you see that all these guys are 0, right? So everything in this upper triangle is 0, right? And so you see that T is diagonal. So T is diagonal, and that's the end. That's the end of that. Okay. So you see that A being normal, right? You see that. Okay, you see that A being normal means that when you take the Schur triangularization, you actually get a diagonalization, right? That this T turned out to be a diagonal matrix. Okay, so you were in fact unitarily diagonalizable. So we're done. So normal turns out to be, being normal and being unitarily diagonalizable turn out to be the same idea. Abel, what is it?
Did you say that T is a real matrix?
No.
So it's not.
No, we don't need it to be.
Oh, so
Yeah.
what if an entry is like I? Then
What is I?
Oh, but that doesn't matter. I mean, I think he meant what if like we have complex entries, but then we already counter that with like you get the magnitude by like multiplying with the complex conjugate.
Yeah, I times negative I is 1.
Yeah.
Right, because you take the complex conjugate, so you get negative I.
The fact that we're assuming it's complex already there.
Yeah. Okay. Everybody all right? Everybody all right? Okay. Okay, so now we're going to go into the last and kind of coolest section, maybe? Singular value decomposition. Okay. So, this is the thing that has a lot of application. It is basically equivalent to something called principal component analysis. Okay, so if you've ever seen anything that involves principal component analysis, what they're doing is exactly what's called singular. It's basically the same thing as singular value decomposition. So let me start off with a question, sort of a dumb question, which is, what does it mean for a matrix to have rank 1? What if a matrix has rank 1? What does that mean? I'm sorry. So what is the rank of a matrix, first off?
The non-zero rows.
The what?
Non-zero rows.
What's the rank of a matrix? It's the dimension of the row space or the column space, right? In other words, the dimension, right? So let's think of it as the dimension of the column space. Okay. So if you have a matrix of rank 1, what does that mean? That means that there is a basis consisting of a single vector, and all the columns of your matrix are multiples of that single vector. Okay? In other words, there's not that much information in your matrix, right? Your matrix is pretty simple, right? You could suppose somebody said, "I'd like you to store this matrix." Okay, it's 10,000 by 10,000. Okay, but you know it's a rank 1 matrix. So if you don't know it's a rank 1 matrix, maybe you have to store every entry, right? So you get 10 to the 8th, right? 10 to the 8th. That's about how much you need to store it. Suppose you know it's a rank 1 matrix. Then you know that there's some basis vector, so you need 10,000 to store that basis vector, right? And then for every column, you need a number, right? Saying what multiple it is, right? What multiple it is. So you get one number, another number. So you get 10,000 numbers. Okay. So in other words, you use 20,000 slots. It's 20,000 numbers to store the entire matrix, which was, if you stored it bit by, pixel by pixel, would have been, 10 to the 8. Okay, so you see that, if you know that your matrix is a low rank, then that allows you to save a lot of space, right? It allows you to compress the information. Okay, so one thing that people do, you can guess that this is something that people want to do, is to take something complicated and then take a matrix that's complicated, like a picture. Say you take a picture and then find a matrix that has low rank and it's close enough to the picture that you can't tell the difference. Okay, so in other words, to find a low rank approximation to your original matrix. Okay, and one thing that singular value decomposition will do is exactly that. It will tell us. It'll say, do you want a rank 1 approximation? Here's how you make the best rank 1 approximation. Do you want to make a rank 2 approximation? Here's how you make the best rank 2 approximation of your matrix, and so on and so forth. Okay, and it's sort of okay. So you won't be able to see this, but in your book. At the end of this section, application 2, they say digital image processing, and they have a picture that says like original 176 by 260 image, and then they say rank 5 approximation. I don't know if anybody can see this, but here's a picture, and this is the rank 5 approximation. Okay, that's actually not so bad for a rank 5 approximation, right? And then they give the rank 15 and rank 30. So rank 15 is here, rank 30 approximation, right? You see that the rank 30 approximation is actually almost indistinguishable from the original picture, right? This is pretty cool, right? So this is how you compress information. Yeah?
So I'm not understanding why the lower rank means less quality necessarily, or less detail.
Well, it means that you're trying to express the entire picture with one vector, right? You've got this one vector, and you're trying to say, I'm going to take my whole picture and find one vector so that every column of pixels is a multiple of that one vector. That's not going to work, right? In general, that's not going to work, right? Yeah.
So like a rank 1 matrix would be like a line, basically, or it would just be like the steady image.
Would it just be like a color?
Well, so rank 1 matrix would be the amount of information in it is just a bunch of numbers, like the coefficients. Like every column there'll be some basis vector. Okay, this basis vector you figure out somehow. Okay, and then there's going to be for every column there's a number indicating what multiple of that you are. So like that. So yeah, it's yeah.
How does that work with multiple basis vectors though?
So then in that case, for each column, you need to store 30 numbers.
A little bit of this vector and a little bit of that vector.
Yeah, exactly. So you'd say, how am I going to come? You're going to have the rank 30 approximation. You've got your 30 vectors over here, and you've got a vector for each row. So for each column, saying what linear combination of these guys do I use to recreate that? Okay. So singular value decomposition. Okay. Okay, so we're going to start off with a bunch of exercises. This is actually something that I might have assigned before. I'm not sure if I assigned it or not. It's 5.2, exercise 13. Anyway, we're going to do it right now.
Just talking about the applications of this.
Okay, good. Okay, so one way of thinking about this is that this is a sort of generalized orthogonal diagonalization. So generalized, in other words, it's for m by n matrices. Okay, so it's going to be some sort of like something like an orthogonal diagonalization, but it's going to be for rectangular matrices. Okay. Okay. Okay, but it's going to have huge applications. Okay, so got 10 minutes. That's enough to do something. So here's the exercise we're going to go through. Let A be an m by n matrix. One, show that if X is in the null space of ATA, then AX is in the range of A intersect the null space of AT. Okay, let me just talk you through it. Okay, after you finish copying. I have to say that you guys write faster than the other class.
You will be better. It's on video.
It's on video.
Cut it out.
Okay. Okay, so let's talk through this. AX, first off, is AX in the range of A? Of course, right? It's AX, right? Which is to say it's a linear combination of the columns of A. It's in the range of A. I mean, it's AX. It's in the range of A by definition, right? So this first part is easy. AX is in the range of A is by definition of range. Right. Second part, is AX in the null space of AT? In the null space of AT, we're asking, so is AX in the null space of AT? That's asking, is ATAX equal to 0? Right? But that's what we assumed, right? We're saying show that if X is in the null space of ATA, then AX is in the null space of AT. But AX being in the null space of AT is exactly saying that X is in the null space of ATA, right? So yes, since X is in the null space of ATA. Okay. Right? Does ATA X equal 0? Yes, because X is in the null space of ATA. Okay, so that's the first exercise. Okay, part 2 of this problem is show that the null space of ATA actually is the same thing as the null space of A. Show that the null space of ATA is the same as the null space of A. Okay, so we'll do this in 2 directions. We'll show that this null space of A is contained in the null space of ATA, and the opposite, that the null space of ATA is contained in the null space of A. So the first part, you say, well, look, if AX, right? If AX equals 0, then certainly ATAX equals 0. Right? So being in the null space of A certainly guarantees that you're in the null space of ATA. Right? Because if AX equals 0, well, certainly ATAX is going to be equal to 0. Right? Because ATAX would be AT0. That's just 0. Okay. So that's this one. Right? The null space of A is contained in the null space of ATA. Now let's do the second one. Say ATAX equals 0. Okay. By part A, we see that AX is in the intersection of the range of A and the null space of AT. Okay, right, by part A, right? But I don't know if anybody remembers the fundamental subspaces theorem. The range of A equals the null space of A transpose
No, yeah.
orthogonal complement, right? Equals the orthogonal complement of the null space of A transpose, okay, by the fundamental subspaces theorem. Okay. But that says then that AX lies in the intersection of NAT and NAT perp
It must be 0.
is 0, right? This equals 0, right? So that tells you that AX equals 0. In other words, X is in the null space of A, right? So being in the null space of ATA means that you're in the null space of A. So this is what we get, right? That the null space of ATA and the null space of A are the same. Okay. Okay. Part C. Part C is to show that the rank of A equals the rank of ATA. The rank of A equals the rank of ATA. Okay. And the proof is, well, I just use part B. So by B, we know that the null space of ATA equals the null space of A. Okay. Now we're going to use the fundamental subspaces theorem again. The null space of ATA is going to be the orthogonal complement of the range of the transpose, right? So it's going to be the orthogonal complement of the range of the transpose of ATA. But what's the transpose of ATA? It's ATA, right? Right? Because you take the product of the transposes in the reverse order. So you're going to get AT times ATT, which is A. Right? ATA is symmetric, is what you get out of this. Okay. And then over here, you're going to get the range of AT perp. Yeah, so taking orthogonal complements of both sides, that gives you that the range of ATA actually equals the range of AT. Right? So taking perp on both sides. Right. So we got that these guys are equal. We take orthogonal complements. We know that subspace perp equals the subspace. Right? Remember that theorem? Subspace perp equals the subspace. So you get this. Right? But the rank of ATA is the dimension of the range of ATA. Right? So we get that the dimension. So we get the rank of ATA equals the rank of AT. But then remember, we saw a long time when we talked about the rank, we saw that the rank of the transpose and the rank of the matrix are the same, right? Right, because one is the dimension of the column space and the other is the dimension of the row space, and we saw that those were equal. Okay, so you get that. You get this result, that the rank of A equals the rank of ATA. And along the way, we got this fact, that the range of ATA and the range of AT are the same. So these guys that I put in boxes are things that we're going to use when we talk about the singular value decomposition. So we need a bunch of these sort of random facts about the relation between ATA and A when we're constructing the singular value decomposition. Okay, that's it. That's it for today.